Right. Good morning. So I want to talk today about topological quantization of sigma xy, and I want to introduce something called Chern number. Okay, last time we introduced and actually obtained equation of motion with Berry curvature, and it was something like this: dr dt is equal to the usual term 1 over h bar cross en of k minus e over c dk dt cross, so this curly b en of k, which is different for each block band. And this dk dt is given by Newton's law, h bar dk dt is equal to some grade, just like gradient here, there is like a gradient in the real space, and there is like some potential, and also this Lorentz force dr dt cross the magnetic field B of r in real space. Here the Berry curvature is given by this b n of k is excuse me, given by del k, this is k, this is Berry connection, and this Berry connection is the usual formula now: u n k del k u n k. Now I want to calculate the current from this resulting from this equation of motion, and the current is to calculate current. So usual current is something like this: J is equal to minus E and V. So this, for this V is, so this term, right? So there will be like usual current, and there will be anomalous current, and I'm considering the case like the perpendicular electric and magnetic fields. But since this term is trivial, I'm not going to consider this. I'm just directly consider this term, and I'm going to calculate whole conductivity sigma xy from this equation of motion. So let's write it. So this J is equal to minus E. I'm going to sum over all vectors, k vectors, and I also consider two dimension because that's the interesting one. At least in this example. So this is 1 over, so let's write this. Like that. And for dk dt, I'm just going to consider like constant electric field, something like that. And okay, like so this minus gradient is going to be force, and the force with minus E charge is going to be plus actually. Actually, it doesn't matter. I don't care about the overall sign, so let's not worry about that. So this one is usual longitudinal current, and this one is going to give transverse or whole current. And that's the interesting one for us. So just to make sure, we are taking E is equal to some E times X, and magnetic field is and we are in like 2D. K is equal to Kx, Ky, and in that case, Berry curvature Bn of K is going to be something Bn, which is going to depend on Kx and Ky, but it's going to be in the Z direction. So something along X direction crossed with something along Z direction is going to be something along Y direction, and that's the contribution we are trying to calculate. So let's calculate this. Jy is equal to, so there is E, so there is E squared I also have this is there is no so this is okay, there is no E over C there, so there is no C there, but there is E because force is minus E times E. Okay, so then I have E, there is like E squared. I also need oh, I see. So this is force is h bar dk dt is equal to force, which is equal to minus E over E. Then dk dt is going to be minus E over h bar E. So now there's like h bar here, but there's no C. So then this is there's like one more E squared over h bar. So this is dk over 2 pi squared, and there is this is along z direction, so there's no vector now, Bn kx ky, and this whole thing is multiplying this E, which is in the x direction. Let me write it like Ex to see the structure, and you can see this is going to be equal to sigma yx. Okay, so Jy is equal to sigma yx times Ey. Then we have sigma yx is equal to this thing. Good. You can see there is like h bar here. There is, let me cancel bar of h bar and cancel this one, and I want to define something called Chern number. Introduce Chern number. So this is C for Chern, and it is going to depend on band index Cn, and this is given by this integral 1 over 2 pi dkx dky bn of kx ky, and this is actually the first Chern number. There are other Chern numbers, but for this particular case, first Chern number is applied. Now I want to calculate this. So this Bn of k is equal to curl. Let me not write curly a's, it's a little bit awkward to write. And a, also these are band dependent. A is equal to I unk gradient unk. Then I can use the Stokes theorem, right? This is curl of something over the area, and I can change it to line integral. Cn is going to be 1 over 2 pi. So now let me write it like dk. This is like a line integral, and it is going to be like enclosing this entire surface dotted onto a n of k. Or this is going to be equal to 1 over 2 pi dr and this object. Now I want to remind you what UNs were. So okay, here is the geometry. So we have a Brillouin zone. So this is Brillouin zone. There is like some reciprocal lattice vectors. Let's call this G1. There is another reciprocal lattice vector. This is G2. If you want, this is minus pi over 2. This is pi over a to pi over a, and this is minus pi over a to plus pi over a. But we could also take it like a non-square. It could be a and b. So the formula is quite general. And the Bloch band is given by psi nk of r is equal to e to the I kr unk of r, where unk of r is equal to unk r plus a. For any lattice vector a, it's periodic. And now I also need to specify, I need to choose a contour, right? There is like there's like some contour, I don't know, let me call it C, but this is different C. Let me write it like curly C. And for this contour, I need to enclose, right? This is integral over whole Brillouin zone, so the contour I'm going to choose is like this. So we need to calculate the line integral along this contour. It's like something like this. You see, I need the values of this A at the boundaries of Brillouin zone, and I need to be careful with the boundaries. And so what happens to psi n k plus g, right? For g is equal to g1 or g2, it doesn't matter. We said psi n k of r. We said if you shift k by g, you should come back to yourself. That's why we call this a torus rather than like any other manifold. And this is effectively identifying k with k plus g for any reciprocal lattice vector. So if you put this in, this is e to the I kr. So this is e to the I gr, right? I split k and g to write it separately. This is u n k plus gr. So this piece is e to the I kr u n kr, and that tells me u n k plus g r is equal to e to the minus I gr u n k of r. So there is like an r dependent shift if you go from this zone to this zone, but it seems like there is no k dependence. But if we use this form, right, if we plug this in to here, so there is like a contribution coming from this edge, like here, another contribution coming from this edge, but these two u's are completely related, and they are related by a k independent phase vector, and there's like a k gradient here. So it's just going to go through the gradient, and e to the ik here is going to cancel e to the minus ik. At the end, the contribution coming from here is going to be the same as contribution coming from here. But this contour is going up, this contour is going down, so they are going to cancel each other. Similarly, if there's like a contribution from here, there will be a minus contribution from here, there's going to be 0. So then C and this Chern number is going to be 0 because of cancellations. And this is obviously wrong, right? This is which is wrong, because we expect sigma xy to be quantized in certain cases. The way to fix this is like consider there is like an arbitrary phase. In quantum mechanics, we said wave function is defined up to a phase, and if rather than this condition, right, as you increase k from k to kg, you come back to not yourself but an overall constant. An overall phase, let me write it like to be consistent, minus I theta. This theta can depend on band. Each band can have a different theta. It can also depend on k, the reciprocal lattice vector, but it cannot depend on r. If it depends on r, you spoil this Bloch periodicity. But as long as it is in this form, the Bloch periodicity is intact and everything is fine. And nobody would be able to tell this additional phase, because that's what the quantum mechanics says us. If we plug this in here, we are going to find un k plus g of r is going to be not only this e to the minus I gr phase, which is this, but also this e to the minus I theta n of k un k of r. So there is like additional phase. And we know if you plug this in, right, this means un k plus g is going to be shifted by this. Let me not write this whole thing. Let me just write the interesting one. So the a n of k is going to go to, you put like additional phase, and in the expression for a there's gradient. The gradient can act on, right, this is like a k gradient, it can act on here or it can act on here. There will be two terms. One term is going to bring you back to exactly the same a n of k, and the second term is going to bring a gradient, theta n of k. I think we have done this exercise. Hopefully that's trivial. Oh, this is there's like minus I here, plus I here. It's going to be a plus. So in that case, so here this piece also cancel in opposite edges, and this is what is left, right? This is left over. So let's just consider this in the contour integral. Then this Cn is going to be, there is like 1 over 2 pi, there's like some contour, dk, gradient in k, theta n of k. But what is integral of derivative? Right, this is integral of derivative. We like had this a lot. It is theta, right? Theta along the boundary, but we have this. So you are just going, starting from here, going all the way around, and you are coming back to yourself. So what you need to do is like you can come back to yourself up to 2 pi because it is like a phase. So then this is 1 over 2 pi times 2 pi, let me call nu, and cancel this, and nu is a positive or negative integer. And from here what we have is like this sigma xy, which was e square over h times Chern number Cn, and it is going to be e squared over h times nu, which is quantized.
We need that hole inside the contour, right?
Can you say again?
We need that hole inside the contour.
Definitely, yes, yes.
But, I mean, this seems like some kind of a well-behaving function. I mean, we didn't define anything.
Exactly. Right? This says like this may be well-behaving function. So right now we didn't specify, right? If it is a well-behaving function, this mu is just going to be 0. There will be no phase picked up. But if there is like a pole inside, right? If you have like 2 pi phase binding, this is going to be non-zero. So in the most general case, this is going to be integer. It doesn't matter how many poles you have here. So you can have 1, 2, 3. This contour integral is just going to pick it up, but only going to give you the number of poles inside.
Number of poles.
Right? And since we didn't specify the problem, and we didn't specify what UNs, what Hamiltonians are, this is the general. This is general for any system.
But I mean, in the typical contour integral, we sum up the residues.
Yes.
So we don't put the number of poles.
No, you can also, right, in the complex integrals, you can deform this contour any way you like, right? You can just go and do this. You can go around, do this. You can deform contours any way you want, but you cannot cross the singularities. If you cross the singularities, that's not allowed. And this red integral is the same as this contour integral. And
What I'm trying to ask is, I mean, how do we know this mu is an integer?
Because it is the phase of a wave function, and wave function has to be single valued, right? If you have a wave function with multiple values, you are in big trouble. It's not a wave function.
But I mean, we say it is r to the some imaginary number.
Yes, yes,
It
yes.
can be any imaginary number. Why
No, so it is a phase, right? We are saying that e to the minus I times, this is like a real number, theta n. If it is imaginary, it's going to decay. So we require it to be a phase. But the phase means if you like change the parameters and come back to the same point in the parameter space, you have to be the same value. But to be the same value, this theta should come back to itself in up to 2 pi modulo 2 pi.
Okay.
Right? And this 2 pi modulo, we generally like say it is like trivial, but it turns out it is actually not trivial. This winding is exactly what we observe in Hall conductivity. So that's the big message, and that's a very good question. Thank you. So now I want to compare this. Let's compare this what we had in the case of a spin 1/2 magnetic field. Let's compare with spin 1/2 in B field. And in that case, Hamiltonian was something like this. H was equal to some H dot sigma, and H was the parameter space. And C, in that case, if you calculate, now it's like a trivial calculation, 1 over 2 pi. There is like some surface, let me call this surface M. And you just integrate over this surface, Berry curvature. And the Berry curvature was, if you remember, something like 1/2 H over H cube, and the surface is going to be something like H squared d cosine theta d phi, and if you do everything, it is going to be, okay, let me pull it aside a little bit. So this is going to be 1 if this H is equal to 0 is inside the surface, and if it is outside, it's going to be 0 otherwise. And the picture is something like this. You have this, what we call the monopole, and it's like Coulomb charge. And you have some surface. And if this surface is enclosing this monopole, you have C is equal to 1. And if this surface is outside like this, right? This is exactly Gauss's law. What comes in from here is going to come out, and the total flux, which is this integral, is going to be 0. And this is actually related to something in mathematics, what is called Gauss-Bonnet theorem. How many people heard of Gauss-Bonnet theorem? Right, it is read it.
Before coming to this,
Uh-huh.
how can we derive 0 from the integral? There's no dh part, isn't
There is no dh. I mean, you need to write it is, this kind of integral is awkward, right? That's the power of Gauss's law. Imagine like you do it like this freshman exercise. There is like a charge here, and you want to calculate total flux in that sphere. Like it doesn't have to be this curved surface, it can be sphere. Right? That integral is quite ugly and it's terrible. It's going to be some kind of elliptic integral. I mean, Mathematica probably can do it, but we never do that kind of integral, right? We never inflict that kind of pain to anyone. We say that, look, what comes in from here is going to come out. I mean, if you have the appetite, you can work with these integrals and try to see if Mathematica gives you 0, but here, mathematics saves you from that trouble. Right? And the Gauss-Bonnet theorem is something like this. If you have a Gaussian curvature, let's call this K. This is Gaussian curvature. I'll give examples to what this is. And if you integrate this Gaussian curvature over some area in some surface M, and if you divide it by 2 pi, Gauss-Bonnet theorem says this is equal to 2 pi minus 2 gm, and this gm is genus of this surface M, or what is called number of holes. So as an exercise, like this is like a trivial exercise, if you are curious, for example, this integral you can do. Exercise for K for like a sphere. Let me just draw like a sphere here. And in sphere you can have like two great circles which are perpendicular, and Gaussian curvature is given by the radius of these great circles, which is 1 over r1 times r2, which is going to be, for the sphere it is trivial, both of them are the radius of the sphere, it is going to be 1 over r squared. Right? If this is the case, K is going to be 1 over r squared, put that in that integral, and that integral is now trivial, right? This is going to be 4 pi divided by 2 pi is going to be 2, and gm is going to be 0, right? The gm is equal to 0 for sphere. Then this C or like this object is going to be 2 for sphere. We can also consider a torus. So this one is trickier. Here's another exercise. If you have the appetite, right? Try to find these Gaussian curvatures for two perpendicular bisecting lines and integrate this. And what you are going to find is, so this is going to give you G2, and we are integrating over this surface M. This is 2 minus 2 gm. How many holes do we have in that case? 1. This is 2 minus 2 is going to be 0. So this is exercise if you want to see if that's true or not. And you can generalize this if you have like something with many handles. Another hole here. In that case, 2 minus 2 gm. In that case, I have 2. 2 minus 4 is minus 2. And the power of this picture is that if you change the surface smoothly, smooth changes on M does not change Cn, right? It is what we call is topologically protected. So you have like some charge, it's emanating this flux, and you have this surface. And suppose you take one piece of this surface and you like push it in a little bit like this. What you are doing is like it is getting closer, but there is also curvature changes. And curvature changes here is like curvature changes there. If it is increasing there, it's going to decrease there, and so on. At the end, what happens is everything just compensates, and the Gauss's law wins, right? Whatever the shape, it's going to be the same answer. So therefore, we are saying that this sigma xy is non-local. Non-local. It is like a global or sometimes topological property of Bloch bands. And when this global property is non-zero, Cn non-zero, these are insulators, right? But they are not insulators like we learn in like Kittel. These are like different kind of insulators. These are called Chern insulators. Chern insulators. Or sometimes they are called topological insulator. So now we can think about let's think about band crossing, which will mean in that case a phase transition, but it's going to be a topological phase transition. So the idea is, if there is like a band crossing, right, like something like this, you can just take two bands and ignore everybody else. Ignore others. In that case, Hamiltonian can be written, the most general 2 by 2 Hamiltonian can always be written like H1, some unit matrix, plus some H dot sigma. And if we are in 2D, this H is going to depend on Kx and Ky. So this thing is trivial, right? You can shift energies up and down, drop this. It's like overall shift, it doesn't matter. And if there is like a band crossing, right, there is like Hx depending on Kx, Ky, and there is Hy and Hz. And for what is the eigenvalue of this Hamiltonian? The E of K, right? You should immediately recognize. You don't have to do the determinant every time you see this. It's going to be plus or minus absolute value of H. And if there's like a band crossing like this, H needs to vanish, and both X, Y, and Z components of X needs to vanish. But this means there are like three conditions on two parameters, right? Three conditions on two parameters is like an overfitting problem. It's not nonsense. So you need to have an additional parameter. Let's call this M. Now this M is the additional tuning parameter where we can picture like if M is less than M star, no band crossing, and if M is equal to M star, band crossing, and if M bigger than M star, again no band crossing. And the picture is something like that. So M less than this tuning parameter, you have these bands. And suppose for the sake of giving an example, this band is like C is equal to 1 and this band is C is equal to 0. I mean, you can pick any other numbers, but as you go to M is equal to M star, you are going to have this band crossing, right? This is what we called monopole in the spin 1/2 problem, right? It is like there's like a monopole emanating this charge, and you need to open this gap to be able to calculate the bare phase. And if you go M bigger than M star, you still have this. But in that case, what can happen is you can have C is equal to 0 here, but this total C coming from these two bands needs to be conserved. So this is going to be C is equal to 1. So this band, lower band, transitioned from topological phase to trivial phase. That's what we call topological phase transition. Good. Any questions? So these are quite general arguments, but there is like one more ingredient that we need to mention. Also, edge bulk correspondence. Now suppose, so we are doing this, like we are going from m less than m star to m bigger than m star in the real space. So what I mean is something like this. Suppose we have, so this is m, suppose this is m star, so this is so this is, let me call this x, this is m of x, and this point here, this point is m star, and suppose here there is like m less than m star, here you have m bigger than m star. The transition can be sharp, but suppose it is like smoothly connecting like this. And this should remind you an example we studied in detail. Does anybody remember? It was like a one-dimensional problem.
At the beginning of the semester.
Yes, this is exactly the case for SSH model, right? In the SSH model, we had like some m, and we put this there, we called it a kink or soliton, anti-soliton. But now we are generalizing that picture. As you go like, right, m less than m star, this side is topological. M bigger than m star, this side is trivial. And as you cross from this side to this side, right, you need to have like this band crossing in the middle, right? There is no way you can go from here to there without this band crossing. So, and what this says is like, so there, like here, so this is the edge, right? There's like one sample here, another sample here, and there has to be like gapless edge modes as you go from like one regime to another, right? So that's what we call bulk or bulk edge or bulk boundary correspondence. So if you have like a topological bulk, it needs to manifest itself through this presence of these edge modes, and we studied this edge mode. We didn't say anything about topology there, but now we have like a bigger reason or like bigger understanding of why they happen, right? You go from one regime to another, and you need to have, by topological arguments, you need to have like a zero mode at the edge.
What is M?
So in the SSH model, we just we called it a gap here, but it doesn't matter. Like it is for any. I am going to give you some examples where what M is, but at the moment it is like a tuning parameter. We are considering like a two-dimensional block band, and in that two-dimensional block band, I need to have kx, ky, but also there's like a third parameter. It is maybe like next nearest neighbor hopping. Maybe you are like biasing like sublattices. One sublattice is a little bit biased from the other, or there is like some external influence. At the moment, we don't care, right? And that's the power of this argument. Without doing any macroscopic calculation, you say that, okay, this has to happen no matter what model you take. Independent of any system, this has to be like this. And M is going to be different from problem to problem, but the picture is going to be like that. And if you have like a topological bulk, you need to have gapless edges. Or another way of saying that, if you have gapless edges, like we had in that example, they are like telling you about topology of the bulk.
Can you again show these phase pictures?
So this one?
Yes. First we start like this, then they connect, and when they get separated,
Yes.
they should look like this, not this.
No, they look exactly like this, but like you know, small changes is not important, right? We said like if you deform this band in like, I don't know, your favorite shape, it's not the point, right?
No, I mean the orientation. The circles one looks up, but I think it's up.
Like this is going up and the other one is going down.
It's not working like that.
I mean, like if you look, for example, SSH model, it is not working like that, right? In the SSH model, if you just go back and check, you have this, and you have this. They are like closing the gap here, and then you have again this. So from like conventional point of view, there is no way to distinguish this face from this face. Nobody other than topologist can distinguish these two, right? And exactly the same the form was like emanating. I think I will come back to this example a little bit on Monday, but let's see if I can do that. But the point is that like you have to let these worries go, right? This is like an argument that saves you from like a lot of calculations, right? Because this is quite generic. Independent of these little details, the most important conclusion is like you have like gapless H modes in topological phases. So let me do one last calculation, and then to give an example, we spent quite a bit of time, and then I will finish it there. Let's consider lambda levels. And let's go back to that. And for simplicity, I'm going to take VR is equal to 0. When there is no external potential, we show that like sigma xy, right? For each one, sigma xy is going to be E squared over H. We have seen that. That means each band is going to have like a Chern number plus 1. But if you have like this like non-zero, you can have other Chern numbers. C is equal to 2, 3, anything is possible. But let's consider this case for simplicity. And I want to consider this so-called Laughlin-Halperin construction. So you have like a disk. And so this edge is Lx. So the circumference of the disk is Ly, and you put a flux which depends on time through the disk. And what we said is like we slowly increase, like slowly or adiabatically increase phi t is equal to 0, 0 to phi t is equal to t to flux quantum, hc over E. And we know the Faraday's law, right? From like if there is like a flux change in the cylinder, there has to be a EMF. This is freshman physics, and right? And EMF is going to be along the circumference of the cylinder, and we can calculate that EMF Vy is going to be, so in Gaussian units, 1 over c d phi dt, and from here we can also use Vy is going to be equal to Ly times Ey, then Ey is equal to this thing times 1 over Ly. And now like we are saying like there is electric field along the circumference, and any current perpendicular to the electric field is going to be Hall currents, and that's the one we are interested. And for Hall current, like Hall current along X, let's calculate the charge right from this Hall current. What we did was like something like that. Q was equal to from 0 to t dt I of x, and this is equal to, okay, let me just copy, but this is So I of x is Ly, right? The cross section is Ly, and current density is Jx. So this is Jx, and this is going to be equal to from 0 to t dt Ly, and Jx is going to be sigma. It's going to be actually sigma y x sigma xy ey, right? I'm trying to match the indices. And ey, okay, I think that's it. So, and ey we calculated here. So ey is 1 over c l y d phi dt, right? We calculated that. At the end, I can cancel this with that, and I have sigma xy 1 over c delta phi, and delta phi we plugged in hc over e. Cancel this with that, and sigma xy we found h squared e squared over h times nu. And what we find is, let's cancel everything and see what this gives us. So this e cancels, h cancels. I think there's what is left is only this nu times e, and nu is an integer, and that means what? That means as you increase the flux from 0 to flux quantum, there is 1 electron, right, per lambda, 1 electron transferred across the sample, right? That's only because nu is 1 for 1 lambda level. But what we said previously was these are the lambda levels, right? In the bulk, we have these lambda levels like this. I don't know, something like that. And our Fermi level is, let's say, here. So we are transferring a charge from one edge to another edge, but the Fermi level is in the gap. And that means that there's only one way to see to have this, right? For this to happen, there has to be this gapless HMOS, there has to be this crossing. There has to be like this, and like this, like this, and like that, right? And what this says is this gapless HMOS needs to match the total sigma xy you calculate. Okay, let me just write one last thing and finish it. Then C total is equal to n occupied Cn, all Chern numbers, right, of the occupied bands, and this is going to be each one, at least in this example, is going to contribute 1, and sum of 1 is going to be an integer, and that integer is going to be manifest in sigma xy. Good. All right. Thank you.